An object is 18 centimeters from the center of a spherical, silvered, reflective, mirrored, glass Christmas tree ornament of 5.6 centimeters in diameter. What is the position of its image, counting from the ornament's surface? Follow the sign rules. Express your answers in appropriate units. What is the magnification of this image? Okay, so start by drawing a picture. So we're going to have an ornament. It's draw a line down the middle. That way it'll be like a spherical mirror where light is going to travel from left to right because light always travels from left to right. All figures are drawn with light traveling from left to right, Cartesian convention. This is going to be our image over here because distance of real image is always negative. We're told we have a diameter of 5.6 centimeters. So let's see here. Radius is then 2.8 centimeters, which means the focal length is going to be half the radius of curvature. So F equals R over 2, which is going to be 1.4 centimeters because we have 5.6 diameter, 2.8 radius because 5.6 over 2, and then half of the radius of curvature is going to be the focal point. And our focal point here is going to be negative because the refractive power of surface that makes light rays more convergent is positive. This is divergent because if you look at it, it hits the spherical mirror and diverges. So it doesn't converge to a point, therefore it's not positive, i.e. negative. Okay, so now we got that. Oh, right in here, distance object. So distance object, we would think 18 centimeters, but we want to do it from the ornamental surface. So we're going to do 18 minus 2.8. Yes, because it's 18 centimeters from the center of the spherical radius, which means that it's 2.8 from the, so it's going to be 15.2 centimeters. There we go. And specifically, it's going to be negative 15.2 centimeters because the distance of a real object is negative. Basically, everything on the left side where the light's coming from is going to be negative. Okay, so now we can use our thin lens equation. 1 over distance object plus 1 over focal point equals 1 over distance image. This is the Cartesian, as opposed to Gaussian, convention of writing the thin lens equation. So solving for distance image, we're going to get distance image is 1 over 15.2. We're going to stick with everything with centimeters, specifically negative 15.2 because it's on the left side, plus 1 over negative 1.4 because we have a diverging spherical mirror. Put this into a calculator. Good old Wolfram, old reliable. So we'll say 1 over negative 15.2 plus 1 over negative 1.4. We'll raise that whole thing to the negative 1 power. And that gives us an answer of negative 1.28 centimeters. That's going to be our distance image. Okay, so now, yes. So we want to know what is the position of its image counting from the surface. And so it's going to be a distance, since we're counting this as the surface right here, 1.8 centimeters. Now, when they say follow the sign rules, they're probably actually talking about Gaussian, because Gaussian is more common in this physics class. So I'm going to say the answer for this is, I'm going to say negative 1.28. Negative 1.28 centimeters, but depending on your convention, your mileage may vary. All right, what is the magnification of the object? Magnification, the formula for magnification is height image over height object, which equals distance image over distance object. So this is specifically the Cartesian formulation of this. For the Gaussian, it's negative distance image, negative distance object. So I'm going to put in our numbers here. Distance image is going to be negative 1.28. Distance object is negative 15.2. And that's going to give us, I'm just going to do 1.28 divided by 15.2. 0.08. 0.08. So 0.08. And then there's no units for that because magnification is a ratio. Okay, so talking a little bit about what some of this means. So the other questions would be asked would be, is this object inverted or not, or real or virtual? So this object is upright because we have a positive magnification. So height above the optic axis are positive. So it's positive above the optic axis. And then real or virtual, it's going to be a virtual object because the distance of a real image is positive. We don't have a positive distance to an image, to the image, we have a negative. Therefore, this is a virtual image. Virtual image, meaning that if you hold up a screen, you won't be able to see anything. The image for this, so if you did the Gaussian convention, you basically get the image over here. And the idea is if you have a object over here, you shine some light on it and it projects the image, and then you hold up a screen on this side of the ornament, you're not going to see the image, which makes sense because this is a solid spherical mirror and light's not going to travel through the mirror, it's going to bounce off of it. And so that's the idea where we're going to have a virtual image, virtual defined as if you hold up a screen, will there be an image actually projected onto it or not? So that is this one. So key idea here is with Cartesian sign convention, these are the conventions, negatives on the left, positives on the right. We still have the idea that a positive magnification means that it's upright as opposed to inverted, and a negative distance image means virtual. A positive distance image means real image, therefore can be shown on a screen. Hope that helped. See you next time.